Okay, in our last video for the chapter, we're going to collect a quick corollary, and then we're going to go into kind of an involved example. So corollary is if we have the Galois group of some extension, some finite extension L over K, and we have a subgroup, the subgroup needs to automatically be finite. I don't know why the book has finite there. It's a subgroup because G in itself has to be finite. Then what? Well, then the degree of the fixed field, which I'm going to write as h dagger, of h under the Galois action. So h dagger in more regular notation is the elements of L fixed by h, is equal to the degree of L over K divided by the order of h. Let me point out something. When the order of the Galois group happens to be the degree of L over K, so this will happen when the extension is normal, finite and normal. Then on the right-hand side, we're going to get the index of H and G, because this degree part, this guy here, is just going to be the order of the group. Okay. So there's some relationships between the degree of the field extension and the index of the subgroup. All right, proof is going to be easy. We have a tower, K contained in the fixed field, contained in L. By the tower law, messed that up. By the tower law, degree of L over K is equal to the degree of L over the fixed field times the degree of the fixed field over K. And so by the theorem, the degree of the oh shoot, I messed that one up. By the theorem, the degree of L over the fixed field is the order of the group. That's what our theorem told us. The degree of L over the fixed field by some automorphism, some subgroup of automorphisms, just the order of the group. And that's the degree of L over K. And the proof follows just by solving. Okay, so the degree of L over K divided by the order of H is the degree of the fixed field over K. So there's not really a lot going on there. All right, cool. This is an important corollary, and we'll see a little bit of it in these examples. You know, I think I'm going to do one example, and then we'll devote one more video to another example. Okay, so sorry, this is not quite the last video yet. Example, this is number 1 in this part of the book. Blue. All right, so let's consider the Galois group of C over R. Now we already know what that is. That has the identity element, and we have complex conjugation. So sigma is complex conjugation. We computed this already in a previous video. Okay, so what's the fixed field with complex conjugation? Well, sigma of x plus iy is just, of course, x minus iy. And the only time that sigma of x plus iy is equal to x plus iy, well, the only time that's true tells us that x plus iy is x minus iy. And that will tell us then, by canceling the x's, that 2iy is 0, or equivalently y is 0. So the fixed field under the Galois action, let's call this G, is just R. And, of course, the degree of C over R is 2, and that happens to be the order of the Galois group of C over R. There's 2 elements in it. There's complex conjugation and the identity element. Okay. So here we see exactly that theorem working out. The proof of the theorem, oh wow, look how long it was. Right, the degree of K over the fixed field is the order of the group. And we see it happening exactly here. In the next video, we're going to do a more detailed example.